All right, so we have talked about what logs are and properties of logs, and we are now going to use those things we have learned to solve logarithmic equations. Now we have two types of logarithmic equations, and this first type we're going to talk about is when a log is equal to a log statement. So our steps to solve these are to condense each log, use the one-to-one property, which means that if log base b of m is equal to log base b of n, then that tells me that m is equal to n. That's our one-to-one property. And then lastly, we solve and we check for extraneous solutions. So when we have extraneous solutions, that's when a log is negative or 0. A log cannot be negative or 0. So let's start with one problem here. Log base 5 of 5x plus 9 is equal to log base 5 of 6x. So first, I want to condense. And there's nothing here for me to condense. So I'm going to go to my one-to-one property. And so if log base 5 of 5x plus 9, this would be my m, log is equal to log base 5 of 6x, that would be my n, then that means m is equal to n. So I can set 5x plus 9 equal to 6x. And then we're just doing some algebra. So I move my 5x over, and I get that 9 is equal to x. And that if I plugged 9 back into either side of my equation, I would not get a negative or a 0. So that is my answer. Okay, let's do another one. Let's look at example number 4. Log base, nothing. So remember, when I have nothing there, that means my base is 10. So log of y plus 5 plus log of 4 is equal to log of 72. So first we want to condense it. So these two logs are being added together. So that's my product log property. So I'm going to have log of y plus 5 times 4 is equal to log of 72. So because I have y plus 5 times 4, I'm going to have to distribute this 4 to both pieces of what's inside my parentheses. So I'm going to get log of 4y plus 20 is equal to log of 72. And now that I have condensed, I'm going to use that one-to-one property. Here, that 4y plus 20 would be my m, 72 would be my n, so I'm going to set those two expressions equal to each other. And again, I'm going to use my algebra, move that 20 over, and then 4y is equal to 52, so I divide both sides by 4, and I get that y is equal to 13. And again, if I plugged 13 in for y, I would not get a negative or a 0, so that is a possible solution. Let's look at one where that we would have an extraneous solution. Let's look at number 3. So it's already consolidated. There's nothing there for me to consolidate, so I can go ahead and set my m equal to my n. So 6 minus 3w is equal to minus 2w. So I use my algebra to solve, and then I get that 6 is equal to w. Now, if I plug in 6 to the expression for w, to 6 minus 3 times w, that would give me 6 minus 3 times 6, which is 6 minus 18, and that's going to give me a negative number. That's going to give me negative 12. So this is not a solution. So this answer is no solution. And we could also plug it into minus 2w, and we would also get a negative number. So that's an example of one where there is no solution. Okay, so that's our first type of logarithmic equation we're solving, when we have a log is equal to a log. The other kind of logarithmic equations we're going to be solving are when we have log is equal to a number, and we have a different set of steps that we follow for that one. The first one is, again, to condense and then isolate the logarithms. So we want all logarithms on one side, all constants on the other side. Then we're going to write the equation in exponential form, and then we're going to solve and check for extraneous solutions. So if you forgot, this is the log base b of a is equal to x, is the same thing as saying b to the x power is equal to a. So in case you forgot how to go from log to exponential form. So let's take a look at number 11 here. We have nothing to really consolidate here, so we're going to go straight to putting that in exponential form. So log base 2, this is my b to the a power, sorry, b to the x power, 6 is my x. I'm sorry. 2 to the 6th power is going to be equal to x minus 4. Now, 2 to the 6th power is 64. So 64 is equal to x minus 4. So I just do my algebra and I get that x is equal to 68. And if I were to plug 68 in for x to my log, I would not get a negative or 0. So that is a possible solution. All right, let's now do number 13. So I have log of 2x plus log of x minus 5, and that is going to be my product property. So I can rewrite this as the log of 2x times x minus 5 is equal to 2. And I'm going to have to distribute that 2x, and I'll get log of 2x squared minus 10x is equal to 2. Now, I don't have a base here, so we assume it's 10. So when I rewrite this in exponential form, I'm going to get that 10 squared is equal to 2x squared minus 10x. And 10 squared is 100. So 2x squared minus 10x. Now what I'm going to end up with here is a quadratic, and I know that because I have an x squared and x and a constant. So when that's the case, I want to move everything to one side of my equal sign. And so I'm going to move that 100 to the other side. And when I do that, it's going to become negative. So I'm going to have 0 is equal to 2x squared minus 10x minus 100. And now I'm going to want to factor this. So I can factor this first by bringing a 2 out of everything, and then that'll make it easier to do our double parentheses on. And so when I factor this, I'm going to end up with 2 times x minus 10 times x plus 5 is equal to 0. So now remember, to solve for x, I have to now set each parentheses equal to 0 and solve for x. And so we are going to end up with 2 possible solutions, and then we're going to have to check to see if one of those is going to give us a negative or a 0. So when x minus 10 is equal to 0, that tells me that x is equal to positive 10. And when x plus 5 is equal to 0, that means that x is negative 5. And if I plug in the 10 to either log, I'm going to get a positive number. So that one's fine. But if I plug in negative 5 to 2x, that's going to give me negative 10. And that can't happen. So negative 5 is not a solution. So our only solution for number 13 is x equals 10. So I want to work one more example where we have to do the quotient rule, since we haven't touched on that quite yet. And let's work number 14. So let me erase this stuff that's in our way. Number 14. So number 14, we're actually going to have to use the exponential rule and the quotient rule, because I have this 2 here and I have subtraction. So to consolidate this, I'm going to have the log of x squared divided by 4 is equal to 2. Now again, I don't have a number as my base, so I assume it's 10. So when I rewrite this in exponential form, I'm going to say 10 squared is equal to x squared over 4. 10 squared is 100, so 100 is equal to x squared over 4. And now I'm using algebra to solve. So I'm going to multiply by 4 on both sides, and I'm going to get that 400 is equal to x squared. So my last step is take square root of both sides, and I'm going to get that x is equal to plus or minus 20. So now to check for my extraneous solutions, I have to plug in plus 20 for x, and that would give me a positive number. But if I plugged in negative 20 for x, that would give me a negative in my log, and we can't have that. So my only solution is x equals positive 20. And that is solving type 2 of our exponential equations, where a log is equal to a number.